Welcome back. Hope you're doing well. Last time we were talking about derivatives and some of the derivative formulas that are useful for us in moving forward and kind of this little trek through calculus that we're doing in a little bit more of a rigorous fashion. Now, the idea was for going through that last lesson was to get us all of the machinery that we needed so that when we move forward to the applications of derivatives, we have a lot to be working with. One of these main applications of derivatives that we begin with in Calculus 1 is dealing with the local max and local min. We've already talked about extreme values having an absolute max and absolute min, which we didn't even need derivatives for. This always exists whenever you have a function that is continuous on a closed and bounded region. But in general, you can also find local extremum now that we have these sorts of functions. In particular, a lot of things happen that are neat whenever our function ends up being differentiable. And that's where a lot of our use of this sort of principle has come into play in the past. And we're going to go ahead and explicate on those things today. At least we'll begin here. We're then going to move on to talk about things like the mean value theorem and L'Hopital's rule, but we'll start here with the local extremum. Let's recall that something is a local maximum at a point if whenever you go around that point in a tiny little epsilon neighborhood around that point, that your function is going to be a little bit less or potentially the same as f of c. You can make this window as narrow as you would like to be. So when you have your picture here, you could write this like maybe something like this. You have your picture of your function, something like this. Here you would have a local maximum at this point, because if I went maybe from point c minus epsilon to a point c plus epsilon here, then I can note that anything around this point, it is the case that f of c is greater than or equal to f of x whenever I'm looking at x inside of this little neighborhood. So this would be an example of a local max. Now notice that it is not an absolute max of this function. Indeed, there are places that are higher than it later on, but that's why this is called local. The information that we're gathering here is not going to be information around the entire function. It's only going to be information here at this point. Now, continuing on, we also have this notion of a local minimum. If we flip the script and say that f of c is less than or equal to f of x for all surrounding points in a particular region here, then this would be a local minimum of this function. And those are the two definitions that we have here for points of local extremum. Now, the theorem of Fermat says that we can actually figure out local information around the function if we're given a single given the derivative at just that point. We don't need derivatives around the entire thing. In fact, only thing that we need to know is that if you have, for example, that the derivative of a point is, well, I should rephrase. If you have a function is differentiable at a point, and that point is the local extremum of the function, then you actually know a good bit about the derivative at that point, that derivative is going to be zero. We'll talk a little bit about some of the opposite directions, what happens when you have a derivative that's positive or negative, but we'll discuss that later on. So here, to go through and do this proof, we only need to check and see what ends up what ends up working with this sort of derivative. And what we're going to use is the fact that we have information that's all around the point. But if we need information around the point, then that's looking at the limit. And the derivative is a very prime example of a limit. For example, if I'm looking at values that are just a little bit past c, let's say, for example, just to begin, that c is a minimum of this function, then we know that any point just past c is going to be a little bit above it. So f of c plus h minus f of c is greater than or equal to 0 whenever h is greater than 0. In that case, this right-handed limit is going to be greater than or equal to 0. Now, this inequality also holds whenever h is a little bit less than 0, too. The only thing that changes is that when you take this value here, now you notice that h is coming to 0 from the left. So now the thing I'm dividing by is actually a negative number, so this becomes less than or equal to 0. However, we do know that our function is differentiable at the point c. That means what? The right-handed derivative and the left-handed derivative must be equal to each other. Well, if this derivative, right-handed derivative, is for sure greater than or equal to 0, and this left-handed derivative is less than or equal to 0, well, there's only one place for them to be equal, and that's at 0. And that is our kind of walkthrough on this theorem. Again, our picture here is that the idea is that when you come in from the right-hand side here and looking at each of these h values, then anything over on this side seems like it has a positive slope of the tangent line, although that's not our definition of the derivative. That is an intuitive way to think about it. Anything to the left has a negative tangent line. Of course, we only need to have the information about things that are local to the point. We don't need information all the way over here in order to be able to determine that. We're only looking at places in the local neighborhood. Hence, why it is so important that we emphasize this to be a local minimum or maximum. Now, Rolle's theorem is the thing that allows us to get existence of something where a derivative is zero. We know that anytime you have a local extremum, you have that the derivative is zero, but we don't know much about the opposite direction. However, characterizing these sorts of points seems like it would be rather useful if our end goal is trying to find maximum and minimum in order to figure out when can we reverse that direction. When is it the case that, for example, when the derivative is zero, that you end up getting a local max or a local min, something like this? And we talk about that a little bit with like the first and second derivative tests in Calculus 1. We'll talk a little bit about the first derivative test later on once we get there. But for now, let's discuss Rolle's theorem and our continuation of continuing to characterize these points, finding places where the derivative is zero. And one place that we can do that is when we have a picture that looks something like this. Let's say that you have a continuous function on the closed interval. This is the first time that we're seeing this formula kind of play out, where you're continuous on the closed interval, differentiable on the open interval, and where f of a is equal to f of b. In particular, it's not necessary for us to try and get derivatives at a or b, respectively, even though limits, right-handed and left-handed limits of those functions should be nice and work well at those points for continuity here. We're just trying to be a little bit more, saying that you only need differentiability on the open interval for this. So our picture here is that we have f of a equals f of b. We have a function where it is defined going from a to b, and we have our picture looking a little bit like this. This is the kind of the standard picture for Rolle's theorem because we have 2 points at which the function is equal to each other, here and here. And you can see here that there is something that has to happen. Even if I don't have a picture that looks exactly like this, if I have something that maybe here's A and here's B, I can have other places for this function to go. But the idea is that at some point on that function, it has to come back down to B. So there is some sort of like increasing, decreasing action going on with this function, no matter how crazy it gets at the beginning or how much it tries to climb or decrease. So whenever you have a function that is continuous on that interval, differentiable on the inside, such that the endpoints have the same function value, then there is going to be a point inside that has a derivative point of 0. And the idea is, how do you do this? Well, by the extreme value theorem, you definitely have an absolute max and an absolute min. And the question is, what happens at those points? Well, the fact is that f of a equals f of b. So it's possible that it could be just a constant function all the way throughout, meaning that there could be just a ton of maxima and minima to choose from. In that case, though, the derivative is 0, so you don't have to worry too much about that. In the case where m is not equal to m, though, where the maximum and minimum are not equal to each other, then you do have that at least one of those extrema is attained at a point C. Well, you have a function that is continuous on the closed and bounded region, so of course you attain maximum and minimum values. Now, due to Fermat's theorem, we know that anything that's an absolute max is also a local max, and hence the derivative at that point is 0. But that's exactly what we're looking for. So that gives us everything that we need. Either case that we're working with, the derivative is equal to 0. A corollary of this is that if you have a polynomial p of x with k greater than 1 distinct real roots, then the derivative has at least that many roots minus 1. Because what happens? You have the real roots are what? Those are places where the polynomial evaluates to be 0. In which case, if you have x1 through xk being your distinct real roots, then in between x1 and x2, Rolle's theorem is going to guarantee a point where your derivative is 0. That's because p of x1 equals p of x2 equals 0. So you automatically satisfy this other condition here. Of course, polynomials are continuous and differentiable everywhere, so that satisfies every condition in that theorem. So that gives us k minus 1 pairings of each of these real roots. Well, when p prime of x is equal to 0, that's exactly what we mean when we say p prime has a real root there. So that gives us the entire corollary. Now, we can use this to try and get us some neat little things here. One of those things is this. Let's say that we're trying to prove that the equation x cubed plus x minus 1 equals 0 has exactly one real solution. Right? We know from our previous theorem that whenever you have n real roots, then you can find at least n minus 1 potential points where the derivative is equal to 0. So here you can see I had 5 real roots and 4 points in which the derivative would be equal to 0. But the question is now not trying to guarantee multiple solutions. I want to prove that this has exactly one real solution. Well, just like we did in our previous example that looks very similar to this, although the problem was slightly different, we can start by trying to prove existence. Now, you might remember that when we did this previously, we were working with the intermediate value theorem. That's useful here as well. The intermediate value theorem, recall, says that whenever I have a function that is continuous, then I can take, if I know two function values on that function, I also know the function takes every value in between those two. So instead of trying to do a cubic equation to try and figure out exactly the x to find for this solution, instead I can go through and say, okay, well, if this is a function p of x, then what is p of 0? Well, p of 0 is going to be 0 cubed plus a 0 minus 1, so this is negative 1. So I know that this function takes on the value negative 1. Now I would like to go through and try and figure out if there is a positive function value for this. If I do, then I know that it hits 0 somewhere thanks to the intermediate value theorem. So I'm just going to plug in 1. Well, that's going to give me the value 1 when I go through and plug that in. So an intermediate value theorem is going to imply that there exists a root of p in the interval going from 0 to 1. So that gets us uniqueness, or rather existence. That gets us what we're looking for there. Now, the idea of uniqueness is going to be tricky, right? Let's say that there exists two real roots of the polynomial p. Then what does our previous theorem tell us? Our previous theorem says that if there exists two, and I'm going to have to be a little bit picky here and say two distinct real roots of the polynomial p, then what has to happen? If two distinct real roots take place, again, I wanted to try and show that there's one, so I'm kind of saying first, let's assume that there's two. Then our previous theorem is going to say, then p prime of x has at least what? It has at least one real root, 2 minus 1. And that's because of the way that this was worded. When you have a polynomial having two distinct roots, the p prime has at least one distinct root. Well, in that case, let's go through and find that polynomial. Maybe we can find something interesting when we try and take this derivative. Well, if I take a look here, I have x cubed plus x minus 1. So if I take that derivative, I get something like 3x squared plus 1. And I automatically see something that is a problem. 3x squared plus 1, 3x squared is always greater than or equal to 0. So 3x squared plus 1 is always greater than or equal to 1. This is a contradiction. There was no way to get two distinct real roots thanks to our previous theorem, because then p prime would have to have at least one real root, but p prime is always positive. There's no place for p prime to be equal to 0. So we have to say, so p has at most one real root, thanks to uniqueness. Since we know that there exists a root and it has at most one, we know that there is exactly one, and so our theorem is proved. All right, so this gets us a neat way to, again, analyze things like polynomials and finding things like roots. This is a very important thing in realms of algebra, is knowing how many roots and where they exist, what type of roots they are, and stuff like this. So having any information on those is a very good thing. Now, there's a version of the intermediate value theorem for derivatives, which is really neat. You might have heard this somewhere, maybe discussed as something like a Darboux property, but we won't be calling that here, and we won't get much into that. But the intermediate value theorem for derivatives is this. Let's suppose that you have a differentiable function, and you have 2 points where the derivative is not equal. Well, then you get that for any value inside and between those 2 points, the derivative has to take on that point. Note, by the way, that this is not saying that f prime is continuous. It is only saying that it has an intermediate value theorem. Recall that whenever we had the intermediate value theorem before, we were talking about continuous functions, and that one shared this very same property. That is the property that is sometimes called the Darboux property. But if a function f is differentiable, it does not mean that that derivative is continuous. Instead, what we get is something a little bit weaker. We get something that says that it has its own intermediate value theorem. So this is exactly what we're trying to say down here. Although the function f is differentiable, f prime need not be continuous on the interval going from a to b. So the intermediate value theorem for continuous functions does not have to apply here. For example, if f prime were already continuous, we could just say, okay, well, boom, intermediate value theorem, we're done. But this actually takes its own proof on this proof for the Darboux property. A corollary of this is that if you have a function defined on an interval which is differentiable everywhere, then the derivative f prime cannot have removable or jump discontinuities. Because think about a jump discontinuity. If you have a function that continues going up this way and then it jumps up to some other place, well, you'd have two different function values on the left and the right parts of your function. So the derivative would have to take on every point in between there in that interval. Well, jump discontinuities definitely are not going to allow that, and so a jump discontinuity is not possible. Now, it is possible that it just oscillated a lot in between there, so that I could get every single value. That was an essential discontinuity, however. So that tells us that maybe we can still have a derivative being discontinuous, but the only discontinuities it would have would be essential discontinuities. I'm going to come back to that theorem in just a second, because this is something that I think is a good thing to kind of be wading through as we go through and discuss this, is the difference between a function that is differentiable and what we call continuously differentiable. We say a function is continuously differentiable if, so this is not continuously differentiable, so maybe I'll write it somewhere else. We'll say that f is continuously differentiable if f is differentiable and f prime is continuous. Note that the name is not saying you can just keep taking derivatives. That would be a different function. That would be smooth. A smooth function has infinitely many derivatives. But something is continuously differentiable if the function is differentiable, and it only needs to be differentiable once. And then f prime, that derivative, is itself continuous. Here's an example of a function that is not continuously differentiable. It's the function x squared times sine of 1 over x, only defined when x is not equal to 0. So in order to get derivatives at 0, we're going to say f of 0 equals 0. Using the product rule, we can go through, find what this derivative is going to be. We get something like this, 2x times sine of 1 over x minus cosine of 1 over x. You can see that this derivative is nice at any point that x is not equal to 0. And indeed, it's actually differentiable at 0 as well. If I plug in what this function f is going to be at the point 0, then I'm going to be looking at something like h times sine of 1 over h, which I know goes towards 0, thanks to the fact that I can bound out the sine of 1 over h. This is less than or equal to h in absolute value. However, if I look at what this derivative is and I ask, is this function continuous at 0? I'm forced to say no. If it were just this part, this function is definitely continuous at x equals 0, but this part is definitely not. There's a lot of oscillations that go on with cosine of 1 over x. This is not continuously differentiable because f prime is not continuous at 0. The limit as x goes to 0 from the right of f prime does not exist because cosine is continuing to oscillate and mess up the function. So there are examples here for where we cannot just use the mean or the intermediate value theorem in showing this theorem. But let's go through and see if we can show that the Darboux property holds for this, namely that there is an intermediate value theorem for derivatives. So here's how we're going to do it. We're going to start by saying, okay, let's start by saying we have f prime of a is less than 0 and f prime of b is greater than 0. Notice that that's not something that is required in the theorem. We only require that the two things be not equal. But the idea is that if I needed to do this in general, then I could shift it, the function so that the derivatives are where I basically want them to be, so that one is negative and the other is positive. Without loss of generality, let's say that f prime of a is negative, f prime of b is positive. Otherwise, I could just apply a negative sign and flip the two. Well, f is differentiable on this interval, so it is continuous. And as the extreme value theorem, again, says you have a closed and bounded region, which your function is continuous on, so it has an absolute minimum point. We're going to call that absolute minimum x naught. So let's start there and let's analyze a little bit about x naught. Now you might actually see where we're trying to get with this. We're trying to show that if you have a derivative less than 0, derivative greater than 0, then there's going to be a point x naught that is a minimum. Well, we know a little bit about the minimum, don't we? We know that whenever you have f prime at least being continuous, right, then you can at least figure out that that is going to be a place where that derivative of that function is 0. But we're going to have to try and figure out a way to get around that a little bit. So let's see if we can deal with the fact that f prime is not continuous and see if we can show that it's still the case that f prime of this x naught is equal to 0. That's going to be our goal. Well, f prime of a is less than 0. So whenever h is sufficiently small, it is definitely the case that f of a plus h minus f of a is less than 0. Our function is decreasing toward this point. Well, what that means is that x naught is not equal to a, because a cannot be the minimum, because f of a plus h for a sufficiently small h is going to be smaller. Similarly, x naught is not going to be equal to b. So x naught has to be in this open interval. Well, what does Fermat's theorem say? Fermat's theorem says, let's go back to it for just a little bit. Fermat's theorem is going to say we can use not the facts that the derivative is continuous, but the fact that the function itself is continuous to help us out here, because that is, oh, that's not Fermat's theorem. Here it is. If our function f is differentiable at a point c, then that f prime of c is 0. And remember, for this one, we are differentiable on the open interval, so we need to make sure we're not at the endpoints here. So if you have an interior point of your domain and f is differentiable at your point c, then f prime of c has to be 0. Well, going back here, we note that this value a is indeed an absolute minimum, not at any of these endpoints. And so because of this, we have that f prime of x naught is equal to 0 by this theorem. So that gives us the point that we're looking for. Whew, okay. So what are we going to do in general? In the case that we have f prime of a is greater than 0, f prime of b is less than 0, we just have to flip the function, essentially. That's another kind of general thing that we can do here. At the end of the day, we are still finding a point there where g prime of x naught is equal to 0. And since one is just the minus of the other, f prime of x naught is equal to 0. And in the general case, we just need to find a way to make our derivatives work the way we want them to. And we just have to, in order to do that, we're going to subtract something from a general function in order to get us into this case. So in the general case, we'll consider the function h of x, which is f of x minus y naught of x. Y naught here again is the value that we are saying we want the derivative to equal this value, y naught. This is the value, by the way, that when I subtract through this, what is the derivative of h prime of x going to be? That derivative is going to be f prime of x minus y naught. Well, if I find a place where h prime has a derivative of 0, then indeed, I'm going to have that f prime is equal to y naught at that point, because I can just move over the y naught from this right-hand side. So only thing that now that I need to show is that there is going to be some point that has a derivative that is positive and another point where the derivative is negative. Then I'm back to one of my previous cases. Well, 0 lies somewhere in between h prime of a and h prime of b, because we know h prime of a was less than y naught, h prime of b is also greater than y naught, and since we're subtracting y naught from both of those as well, we're going to get that one is negative and one is positive. And so we're done. That gives us everything that we need. A neat little way to show that the intermediate value theorem does work for derivatives, even if the derivative is not necessarily continuous. Now let's use this and get to another theorem that now is going to require us to talk about, excuse me, I had to sneeze there. I'm so glad I can pause these recordings. To talk about what happens when I really need my function to have a derivative for, and that is going to be with the mean value theorem. The mean value theorem is going to be important because the derivative gets involved in the equation that we're working with here. So there's no way to even write this equation without thinking about what, well, is my function going to be differentiable here. The picture for the mean value theorem you may have seen before. That picture for the mean value theorem is usually you have a function that has some f of a and f of b value, and you're connecting them in this following way. So you got your function like this. And what I can see here is that with this particular function, it can continue to go on from one point to the other, but I'm only considering it going from point A to point B. And I have drawn a secant line through that function going from point A to point B right here. The mean value theorem says this, that there's going to be a point somewhere else on this function where if I draw the tangent line at that point on the function, then the slope of that tangent line is exactly the slope of the secant line. We know the slope of the tangent line to be f prime of some point c, here c being some point inside of the interval going from a to b. And we know that this formula is the difference in y's divided by the difference in x's whenever I'm talking about the slope of a secant line. So we're saying that there is going to be a point where these two things are equal. In order to get rid of fractions, sometimes you see the formula written as multiply times b minus a on both sides. But if you do that, then this is the exact same formula. So this is the mean value theorem. In some sense, you are getting a point that reaches the average slope of the entire function. That point has a derivative where the slope of that tangent line matches the entire slope of the secant line on that function. The way that we're going to do this is we're going to try and take this function and utilize Rolle's theorem. The difference between this function and Rolle's theorem, however, is that Rolle's theorem asks for f of a and f of b to be the same. You need to have the endpoints being the same. However, once you do get there, you can see kind of what we would do. Now, if you draw a line between f of a and f of b, that's a horizontal line because the y values are the same. There always exists a point in the middle there where the derivative is going to be 0, and hence 0 being the average value on that function, the average slope of it, that's going to get you everything that you need. But the question is, how do we get there? How are we going to get this function to generalize to working with something that works with Rolle's theorem? And the way that we're going to do it is we're going to construct a new function. We're going to construct a function h naught of x. And let's take a look at what this is. The function h naught of x is going to be this. You're going to take f of a, so that's the endpoint there, times b minus x divided by b minus a, plus f of b, which is times x minus a divided by b minus a. We can analyze a few things about this function, namely that h naught of a is f of a and h naught of b is equal to f of b. And we can also notice that h naught is a differentiable function. In fact, if I take its derivative, I get f of b minus f of a divided by b minus a. So actually, what do I notice about this? H naught prime of x, this is a line connecting a comma f of a. So let me write this over here. This is a line that is connecting the points a comma h of a, f of a. Because we know that at a, it is this y value is f of a, and b comma f of b. And the reason that I know it's just a line is that take a look at this derivative. This derivative has no x in it at all. It is a constant derivative. So this is a line connecting those 2 points. In fact, I can tell you exactly what that line is in this picture. This is h naught of x. Here, the function f is the function is the blue line here, and the red line underneath is h naught of x. So here's what I'm going to do. I'm going to take the function f, and I'm going to bring it down. I'm going to subtract the function f by the function h naught. Well, what happens when I do that? At this point, if I'm subtracting h naught from f here, then I know in particular that a and b are both going to be equal to 0 for the function f minus h naught. Now, above that, you can see that there's just kind of like a little hump here for me to be working with. But what do I have now? I have a function that now seems to be utilizable in the context of Rolle's theorem, because I have something that is a differentiable function as a subtraction of 2 differentiable functions, f and h naught, and I have something where the endpoints both have the same y values. So this is exactly where I'd like to be, because now I can start utilizing Rolle's theorem. So we're going to do exactly that. We're going to take the function h to be f minus h naught, and note that the 2 endpoints have the same y value, in this case, the y value of 0. Well, by Rolle's theorem, there's going to be a point where h prime of c equals 0. The only thing I need to show is that now the fact that I found that value c is that that value c satisfies this equation. Well, let's try and figure out what f prime of c is in terms of h prime of c. Well, we've got the formula for what h naught is, and we have the formula for what f is. So we can write the formula for h prime of c in terms of those 2 things. And what is that derivative? Well, would you look at that? If this is equal to 0, then we get exactly what we're looking for, because I can just move over this quotient over to the right-hand side. and I get exactly the formula that I'm looking for. So a neat little trick there, a way of moving a function down in some sense to make it so that the function values both have the same, are both the same and both equal to 0 at the endpoints, so that Rolle's theorem can apply, and then the mean value theorem says we could do this for any 2 points because we can just move the function back up. Now that we've done this, we can start going back to monotonic functions and utilizing some more of our intuition with respect to some of these things. So for example, let's say that you have a function that is continuous on the closed interval a to b and differentiable on the open interval from a to b. Well, now we can talk about things having to do with non-decreasing and non-increasing on these functions, as well as strictly increasing and strictly decreasing. This is essentially where we talk about the first derivative test taking place. Because if a function is non-decreasing, we can say that that's true if and only if f prime is greater than or equal to 0. And f is non-increasing if and only if f prime is less than or equal to 0. Notice, by the way, that these are all happening on intervals. So we're not actually running into the case of f of x equals 1 over x that we were talking about before. Remember, this one is not a decreasing function, strictly decreasing function, non-increasing. It is none of those things because, and this doesn't break anything here because we are having our functions be defined on intervals. Here, our function would not be defined at 0, so that would not give us an interval of domain. Now here we have if f prime is greater than 0, that f is strictly increasing on a to b. And similarly, if f prime is less than 0, f is strictly decreasing here. All right, so this gives us some neat little ways of kind of connecting these things. This is exactly what we do when we do the first derivative test. Finally, f is constant if and only if f prime is equal to 0. And there's a neat little proof here that you can see uses the mean value theorem. Because whenever x2 is greater than x1, f of x2 is greater than f of x1 whenever you're looking at a strictly increasing function. In those cases, f prime of c would be forced to be positive in order to make this equality hold. So that's a neat little way to kind of see this sort of stuff go through. All right, so everything else kind of follows through for a lot of the statements that we've seen already from before. Now, a neat little hidden gem with all of this is that sometimes these derivatives can now be used for approximation techniques. Let's say, for example, that I want to write e to the x in a simpler way, at least get a lower bound for what e to the x is. And this is sometimes useful because maybe you're more interested in something with polynomial growth or just showing that this has more than growth than a certain polynomial, rather than trying to show that something is actually following an exponential model. This can happen in many different applications, which you're doing regression or you're trying to model pieces of data. Then something you might be interested in is trying to figure out, okay, how can I prove that I have specific bounds for one function or another? I could bound x plus 1 above by e to the x, for example, or e to the x below by x plus 1 whenever x is not equal to 0. Well, what's one way that we could do this? Well, we could look to see what happens. Well, first we could start trying to see, like, where is this function equal? Let's start by taking the function f of x being the subtraction of these two things, e to the x minus 1. Where is it that this function is equal to 0? Well, it equals 0 whenever x equals 0, right? So we note that f of 0 is equal to 0 here. But what's happening everywhere else on this function? Well, for example, if I look at places where x is greater than 0 and I take this derivative, I'm looking at things like e to the x minus 1. And I might notice that as long as x is greater than 1, and then implies that e to the x minus 1 is greater than 0. That's because e to the x is greater than 1. That's something we discussed back in our monotonic functions section. On the other hand, if x is less than 1, and here we can either use the fact that 0 is inside of here, but we don't even need to use that. We can just say if x is less than 1, then this derivative, e to the x minus 1, is actually less than 0. But what do we know about these derivatives? If a derivative is strictly decreasing, or a derivative is less than 0, then we know that our function is strictly decreasing up to that point. On the other hand, if your function is, or your derivative is greater than 0, then your function is strictly increasing. So if we were to draw a picture of this, what would it look like? Well, we have at f of 0, you have something that has 0 at that point. And you have that the function is decreasing all the way to that point. You also have that it is increasing away from that point. Something I notice about this function f is that f of x is greater than 0. Well, if f of x ends up being greater than 0 here, then I actually know that because of the definition of x, e to the x minus 1 is greater than 0. Of course, this is going to be when x is not equal to 0. We're excluding this point here. But then if I go through and resituate that inequality, I get exactly the expression that I'm looking for. This is more or less what is being said here in this little prompt. We can do a similar thing here with log of x and showing that log of x is less than x minus 1. Here, we are doing a similar thing of attempting to find what these functions look like and trying to structure them to look the way we want them to. For example, here we're going to start by looking at e to the power of on both sides and then end up figuring out what we can do past that once we take derivatives. Here's another problem. Let's find the minimum as x is greater than 0 of x to the x. Just looking at this function, it's hard to imagine what x to the x is going to look like. So why don't we try and analyze it instead using the derivative of this function? Well, right now, x to the x is not an easy one to take the derivative of, at least not in its current form. So what we're going to do instead is we're going to write this as a slightly different form of a function. For now, let's write f of x equal to x to the x. And notice that if we took the log of both sides, then we would have that log of f is equal to x times log of x. In particular, that means that we can rewrite f as e to the x log of x. This is something a little bit easier to take the derivative of because I have a chain rule. There's a power on the inside of the base of an exponential function. And then I have a product rule to take for x log of x. Might be a little bit more complicated, but at the end of the day, I can find its derivative, and once simplified, I get something like x to the x times log of x plus 1. Question is, when is this positive? When is this negative? Well, x to the x, if I'm looking at values, say, that are greater than 0, which is what I'm doing here, x to the x is going to be positive. That's good. I know at least bank on something here being positive, and that's going to be x to the x. Log of x plus 1, on the other hand, not always positive. That's because I know, for example, that log of x, log of 1 is equal to 0. And then if I go down low enough, log of x actually approaches negative infinity as x goes to 0 from the right. However, if I look at what happens, where is it that this derivative is actually 0, then I find out that this is going to be where log of x is going to be equal to negative 1. Raising both sides to the power of e to the power, and then putting e in the base, better to say, I see that the derivative is positive as x is greater than 1 over e, and the derivative is negative as x is in between 0 and 1 over e. Well, what is that going to tell me? The derivative is negative going toward the point, and positive going away from the point. Is strictly increasing coming to it, strictly increasing going away from it. Very much like our first derivative test. That tells us that we have a minimum at this function at f of 1 over e, which is going to be e to the negative 1 over e once simplified. Now, before we go on into our very last kind of main application here for derivatives, we want to talk about something called Cauchy's mean value theorem, which right now is going to look a little bit strange. It's going to look like the mean value theorem, but you just stapled another function onto there. If functions f and g are continuous on the closed interval going from a to b and differentiable on the open interval from a to b, then there exists a point inside that open interval such that g prime of c times f of b minus f of a equals f prime of c times g of b minus g of a. Something that might help you see that this looks a little bit by the mean value theorem is to try and divide both sides by b minus a. If you do that, then you start looking at this and saying, oh, wait, this kind of looks like if I just isolated this part right here, this looks like the mean value theorem. And if I just isolated this part right here, then this looks like the mean value theorem again. It's like you're applying the mean value theorem. The only difference, and the reason that we can't just say, okay, use the mean value theorem on f and g and just multiply the two functions you get together, is that here you are getting the same exact value of c for f and g in this function. If you had used the mean value theorem twice, you potentially get two different values for c. So multiplying two instances of the mean value theorem together does not necessarily work. Now, the usual mean value theorem also is a particular case of this theorem. If I had just said, okay, instead of looking at two arbitrary functions, if I had said, let g of x equal x, well, then this is just b minus a, and then g prime of x is going to be equal to 1. So here you can see that I have the formula f of b minus f of a equals f prime of c times b minus a. If g of b is not equal to g of a and g prime of c is not equal to 0, then I can actually rewrite this formula in the following way. I can write it as f of b minus f of a over g of b minus g of a equals f prime of c over g prime of c. Now, this is actually a prime setup for us here, because this is something that maybe we have seen before. Taking the derivatives of a numerator and denominator happens a lot when you have an indeterminate form when you take a limit. That is exactly the notion of L'Hopital's rule. This is a big part of where Cauchy's mean value theorem becomes useful. Now, it's not the only time that Cauchy's mean value theorem is useful. Sometimes you are parameterizing a curve. You're not looking just at a function anymore, but maybe you've got like a swirl, or something like this that you're parameterizing. If you find mean values on these things, then you can kind of look on Wikipedia right after this if you would like. I found it kind of neat to look at the page for this. You can find that Cauchy's mean value theorem says that there's going to exist a point somewhere on that curve that is either stationary, which means that its derivatives with respect to either of the parameterized functions that you use is going to be equal to 0 on both of those parameters, or you're going to get that the line connecting the endpoints of that swirl there's another point that has the same slope of it on that function. It's a neat little thing, and I recommend if you want to see anything more about the Cauchy's mean value theorem, that the Wikipedia page is a neat little link to try and check out there. Now, Cauchy's mean value theorem has a proof that utilizes the mean value theorem itself. Since we've already proven the mean value theorem, we're free to use it. So we're going to define a function that's going to allow us to allow stuff to fall out and get what we want. So we're going to use the function h of x, which is going to be this. It's f of x times the difference in the y values of g minus g of x times the difference in the y values of f. Well, first, h is a continuous function. We're just putting continuous functions together and multiplying them by constants. Furthermore, I can say a lot about h of a and h of b. H of a is going to be, once everything cancels out, and indeed things do cancel out nicely, f of a times g of b minus g of a f of b. H of b is going to be f of b times g of a. Notice the similarity here and here. And plus g of b f of a. Notice the similarity between here and here. In fact, the two values are going to be equal to each other. If that happens, then Rolle's theorem says there's a point in which the derivative of this function is 0. But you might have noticed that the derivative of this function gives you exactly what you would like. If you find that function's value of c, then you get to just plug in that value of c, and notice that if h prime of c is equal to 0, then this whole thing gets you a value of 0. So moving over the second term, you get the formula. So where that is useful is going to be in L'Hopital's rule, which is useful to compute limits of quotients in cases where most other limit theorems will not apply due to indeterminacy of the form that you're given. Something that's 0 over 0, infinity over infinity are the two forms that usually you see L'Hopital's rule given in. So here's the theorem and the conditions that are useful in order to prove it. Let's start with a real number or negative infinity to infinity. This is the place where x is going to be approaching. X can approach a real number, a, or it can approach negative infinity or positive infinity. Any of these is going to be fine. Now take I to be an open interval such that either a is in the interval or a is an endpoint of it. So it's approaching, say, from the left or the right. Suppose that functions f and g are differentiable, that they have g and g prime are both not equal to 0 for all x, at least potentially outside of that point A. And suppose further that the limit of f of x and limit of g of x is equal to a, and that they're both equal to each other, essentially saying that if I were to look at this value down here, that either I'm looking at 0 over 0, or infinity over infinity, or negative infinity over negative infinity, when I'm attempting to, plug things in. Then, if the limit of f prime over g prime exists, and that can be infinite here, then I can say for certain that the limit of f over g is the limit of f prime over g prime as I approach that point. So notice all of these conditions here. By the way, each of them are strict. One thing that is interesting to note is that you need that the limit of f prime over g of prime exists. The reason for that is this. You could have a limit of this form that actually exists. But the limit of f prime over g prime does not. In that case, of course, these two things are certainly not equal. So that is one condition that is necessary for L'Hopital's rule, is that the limit f prime over g prime exists. So let's go through and see what this kind of looks like for the case of 0 over 0. Now, there is a case here for infinity over infinity, which does kind of fall out a little bit from the 0 over 0 case, but there are still some picky things to be concerned of in the proof for that case. Now, there's a lot of similar rules that have to be used here because technically we're doing a lot of different things all at once. If you were at an endpoint of your interval of domain, then you're only doing a one-sided limit. Otherwise, you're looking at a two-sided limit, unless you're looking at infinite limits, which we're also kind of trying to umbrella here in this proof. In the case of 0 over 0, we're going to try and extend f and g to be defined on the point A, because remember, we said the functions did not need to be defined at the point A, because limits don't care what happens at a point A, by letting f of a and g of a both equal 0 at that point. Well, that was what their limiting values were, so that makes f and g continuous on this particular region. In fact, it also makes them differentiable. So by the Cauchy mean value theorem, now that I get to use it because it's continuous and differentiable, there exists some value c sub x. Notice that this value depends on this value of x that I'm choosing as we go from a to x. Because notice here we're approaching a from the right, such that g prime of c sub x, this is all Cauchy's mean value theorem, so this is all that formula here. We have that c sub x is inside of both of those two derivatives. Well, what's happening here? If f of a and g of a are both equal to 0, then this part goes away. Then I can start dividing some things together, and it's legal for me to divide them because here we are assuming that g of x is not equal to 0. So that's allowed for me to do. Sorry, I should highlight that. G of x is not equal to 0 up here in this theorem. So it's okay for us to divide there. We also know that g prime of x is not equal to 0 as well. We don't know much about g prime of c of x, but we can always say, okay, g prime of x is going to be somewhere here, right? And the only way that we don't have any jump discontinuities here. So there's going to be at least some neighborhood here where I can say, okay, eventually this is going to be all positive or all negative here. So that's the only thing that we have to be careful of in choosing the c sub x and making sure that this derivative is non-zero. Well, since c sub x is inside of a of x, c sub x is going to approach a from the right as x approaches a from the right, because this interval is continuing to grow smaller and smaller. You're looking at the interval going from a, and here's x, and c sub x is somewhere inside of here. As you change as you change x, c sub x might change as well, but notice that really as x approaches a, there's nowhere else for c sub x to go except toward a as well. So that means that these limits are able to be interchanged. I can, instead of looking at c sub x and saying that goes to a, I can say c goes to a from the right. And if I do that, then that's exactly what I get. Just changing out the labels now for c equal to x, this gives me the formula for the 0 for 0 form. Some examples here. 1 minus cosine of x over x squared. We get a lot of very neat and interesting L'Hopital's rules by looking at trigonometric formulas. 1 minus cosine of x and x squared, for example, both limit to be 0 as x goes to 0. Oh, rather, they both go to 0. Then if we take the derivatives, we get sine of x over 2x, which, by the way, we know the limit of. This one's going to be 1/2 times 1. But we can also just go through and apply L'Hopital's rule once again, because if we show that this limit exists, then the limit of f prime over g prime is going to exist, and hence the limit of f over g will exist as well. So this gives us what we need for 1 minus cosine x over x squared. We could also do sorts of theorems doing with x to the alpha log of x, either going from 0 to the right or going off toward infinity. And here you can see us kind of walking through each of those sorts of things. Now here, notice that what we're doing is we are starting by looking at something and saying, wait, this is not actually in the form 0 over 0 or infinity over infinity. For example, here alpha is not equal to 0, so x to the alpha as I approach 0 from the right, x is going towards 0, so x to the alpha is going toward, well, 0 as well. Log of x, on the other hand, is going toward negative infinity as 0 comes in from the right. So this is a form 0 times negative infinity, which actually I don't know very much about. But you may recall that what we end up doing in these sorts of situations is we start by trying to take a look at what happens when I divide by the reciprocal. of x of alpha. If I do that, then this becomes something that's more of this form. Now that is something that I could use L'Hopital's with. Essentially, that's what we're seeing here in this formula here. So if we go through and take those sorts of derivatives, then we're going to get this sort of kind of falling out when we take all of this stuff. The idea is that log of x, even though it goes toward negative infinity, as we could approach 0 from the right, its derivative is 1 over x, which is a lot easier to maintain and work nicely with. So by L'Hopital's rule, I can get a lot of neat little derivatives here. As particular, by L'Hopital's rule, if x is going to 0 from the right, then this function is going towards 0 as alpha is greater than 0. And if I'm going to x towards infinity and alpha is less than 0, then I also have that this quotient is equal to 0. But that does it for us today. We've seen some good examples here of the mean value theorem and how its applications can be employed together with the L'Hopital's rule. All of these are excellent applications of derivatives. And you might be already thinking, oh boy, have we seen them all? And the answer is no. We have not even started to scratch the surface for all of the ways that the derivative can be applied. We're only going to get to go through a few more in this particular week, but we're still not done in just the content that we're going to be covering. But that will do it for me today. Thank you so much. Have a wonderful day.